Dakota Territory, 15th of October, 1880, Weather Bureau station summaries for eastern Dakota recorded 30 to 36 inches of snowfall in under 48 hours, followed by a temperature drop from 38 degrees Fahrenheit to minus 18 degrees Fahrenheit by the third night. Homestead diaries from the same week note kerosene frozen, livestock unable to reach feed, and doors rendered immobile by drifted snow and ice. County repair ledgers list the most common failures: split door jambs, torn hinge straps, and crushed sill planks. Most cabins relied on flat thresholds cut from softwood planks with doors hung flush to the exterior wall. The design allowed quick construction and swelling tolerance, but created a lever point at the floor. Pressure applied low did not meet resistance, it multiplied it. One homesteader altered the geometry. He raised the threshold into a rounded lip and set the jambs back behind it. The winter would test whether shape mattered more than strength. Fresh adze marks scored the surface of a softwood sill plank outside a newly framed doorway in Halleck Township area, Dakota Territory, spring of 1879. Bark still clung to the underside. The plank measured 8 inches wide, 1 1/4 inches thick, cut from local pine. It lay flat against packed earth, flush with the exterior wall line. Homestead manuals issued through railroad land offices during the 1870s emphasized construction speed above all else. A serviceable door could be framed, hung, and latched in a single afternoon. Typical specifications called for 3/4 to 1 inch of floor clearance to accommodate seasonal wood swelling, flat sill boards to simplify leveling, and 2 strap hinges, either forged at local blacksmith shops or shipped by rail freight. Freight tariffs made iron expensive. A matched pair of strap hinges cost $1.25, delivered to a rail depot, representing roughly 3 days' wages for common labor. Sill planks cost 15 cents. The economic logic was clear: minimize iron, maximize timber. Doors were expected to close, shed rain, and accept a latch. Resisting sustained force was not part of the design brief. The flat threshold geometry created an unintended structural vulnerability. Any horizontal pressure applied at or below knee height, from boots, livestock shoulders, drifted snow, or ice expansion, acted on the door leaf as a lever. The bottom hinge became the fulcrum. The flat sill provided no deflection surface. Force multiplied rather than dispersed. Store ledgers from rail-served settlements throughout Dakota Territory show a consistent pattern during the 1880s. Hinge sales spiked each winter, declined through spring, then spiked again the following winter. Door plank sales remained relatively stable. The pattern indicates that hinges failed far more frequently than door leaves, a reverse of what structural logic would predict. Iron should outlast wood. It did not. Homesteaders treated door failure as routine seasonal maintenance, not a design flaw requiring correction. Budgets included hinge replacement costs. Repair schedules assumed doors would need attention twice yearly. The expense and labor were accepted as unavoidable overhead, like roof patching or chinking repair. Grit packed into the knuckle joint of a bottom door hinge, frozen solid by mid-January of 1880 in a Missouri slope settlement cabin. The hinge was 1 season old, replaced the previous spring. The strap showed no cracks. The pintle remained straight. Yet the door bound tight against the jamb, immobile until an axe blade was used to chip away ice from the exterior base. County damage reports and homestead insurance claims filed during the winter of 1879 to 1880 reveal a consistent pattern. The majority of structural door failures involved damage concentrated at the bottom hinge and the sill. Upper hinges rarely failed first. Locks and latches seldom showed stress damage. The destruction began at ground level. Technical analysis explains why. When horizontal force from a boot kick, livestock pressure, or ice expansion contacted a door below the midpoint, the flat threshold acted as a fulcrum. The door leaf became a lever arm. The bottom hinge endured tension stress perpendicular to its design strength. Hinge straps pulled away from wood fibers, pintles bent, screw heads tore through softwood jambs. The expectation among frontier builders was straightforward. If hinges failed, install stronger hinges. Blacksmiths responded by forging heavier strap hinges with thicker iron stock and longer screw penetration. Hardware catalogs from the 1880s show a steady increase in hinge dimensions and weight. A standard strap hinge in 1875 measured 10 inches long with 3 screw holes. By 1882, common specifications called for 14-inch straps with 5 screw holes and doubled iron thickness. The outcome contradicted the expectation. Heavier hinges failed as frequently as lighter ones. Failure rates did not correlate with hinge strength. Damage reports show that doubled iron thickness delayed failure by days, not months. The problem was not insufficient material strength. It was uncontrolled leverage. A telegraph station maintenance log from Fargo, Dakota Territory, documents repeated hinge replacements following storm events during the winter of 1879 to 1880. The station door required new hinges in November, again in January, and again in March. Each replacement used progressively heavier hardware. Each failed within weeks. The final entry notes: replaced entire door frame, hinges sound. The pattern appeared across the northern plains. Stronger hinges absorbed more force before failing, but they still failed because the geometry that created the leverage remained unchanged. A homesteader worked a hardwood offcut with a draw knife on a late summer afternoon in 1880, northern plains. The wood was ash, salvaged from a broken wagon wheel hub. He shaped it slowly, removing material in thin curls, rounding the forward edge into a smooth arc. The piece would become a door threshold, but not the kind described in homestead manuals. Agricultural journals published during the 1870s and 1880s occasionally referenced a construction principle common to multiple building traditions. Deflection defeats resistance. Rounded structural members shed force rather than absorbing it. Raised elements convert horizontal pressure into vertical load, which foundations and walls manage more effectively. The principle appeared in fencing manuals discussing post caps, in bridge engineering notes on rounded bridge piers, and in accounts of indigenous construction methods throughout the plains and woodland regions. The homesteader applied this principle to the doorway. Instead of laying a flat sill plank flush with the wall line, he designed a threshold that rose 2 1/2 to 3 1/2 inches above the cabin floor. The exterior face was rounded into a convex curve. The door jambs were set back 1 to 1 and 1/2 inches behind the lip of the threshold, creating a recess. The modification changed the mechanical relationship between door and threshold. Horizontal force striking the door no longer found a perpendicular surface at ground level. Instead, it contacted a curved surface that redirected the energy downward and outward. Boots slipped rather than gaining purchase. Livestock shoulders slid off the rounded lip. Ice expanding upward from the ground fractured outward rather than prying inward against the door jamb. The expectation embedded in standard frontier door construction was that a door stopped force at the lock or crossbar, the point where strength was concentrated. The reality documented. In damage reports showed that failure began at the floor, where no strength was concentrated at all. Construction manuals specified hinge placement, door thickness, and lock quality. They said almost nothing about threshold geometry. The assumption was that a threshold was a passive element, a piece of wood that kept dirt from entering. The homesteader's modification reframed it as a structural defense, the first component to encounter force and the primary means of redirecting it. The change required hours of work, not weeks. One afternoon with a draw knife, an auger for pilot holes, and a handful of wrought nails. Winter would determine whether the geometry mattered. The grain of hardwood showed clearly where a new threshold met packed earth outside a doorway in Dakota Territory, September of 1880. The wood was oak, salvaged from storm-damaged freight pallets at a rail depot. It measured 4 inches wide, 3 inches thick, 10 inches longer than the doorframe to allow tenon jointing into the jamb posts. Material selection mattered significantly. Hardwood, oak, ash, or elm resisted compression and wear better than softwood, particularly at the exterior edge where boots and shoulders made contact. Softwood thresholds functioned adequately if thickness was increased to 4 or more inches to compensate for reduced density. The timber needed to be seasoned, not green, to minimize future shrinkage that could open gaps at the jamb connection. The exterior face was shaped into a radius using a draw knife and smoothed with a spoke shave. The curve started at the top surface and swept down and outward, ending approximately 1 1/2 inches forward of the vertical jamb face. This geometry created a deflection surface. Horizontal pressure found no perpendicular purchase point. Force that would have acted as a lever against a flat sill simply slid downward along the curve. The jamb setback was equally critical. Door jambs were mortised into the threshold and set back 1 to 1 1/2 inches behind the exterior lip. This recess meant that when the door closed, its exterior face sat behind the rounded threshold edge. Pressure applied to the door surface could not reach the jamb directly. The threshold lip intercepted it first. Construction sequence determined whether the modification worked. The threshold was installed first, bedded firmly on foundation stones or packed earth, leveled precisely. Jambs were then mortised into the threshold and raised, maintaining the setback dimension. The door was hung last, fitted to the recessed jamb faces. Reversing this order, hanging the door before setting the threshold geometry, negated the structural advantage. The expectation documented in period construction manuals treated thresholds as passive elements, meant only to shed water and keep dirt out. The outcome recorded in damage reports showed that thresholds could function as active structural components. The first defense against multiple failure modes. County repair ledgers from late 1880 show an interesting anomaly. Homesteads that adopted the raised threshold design ordered replacement hinges at less than 1/4 the rate of comparable structures using flat sills. The hinges themselves were identical. The geometry surrounding them was not. Load paths had changed. Hinge stress decreased even though no metal component had been modified. Ice feathered upward along a door seam elsewhere in Dakota Territory, November of 1880. The crystals grew in delicate branches, following the grain of the wood, forcing the planks apart. By morning, the door jamb showed a visible crack. By afternoon, the crack had widened to 1/8 inch. The door could no longer close properly. Weather station notes from the northern plains during the 1880s describe repeated freeze-thaw cycles throughout late fall and early winter. Daytime temperatures rose above freezing, melting accumulated snow. Nighttime temperatures dropped below 20 degrees Fahrenheit, freezing moisture trapped in wood grain and joint gaps. Each cycle expanded ice volume by approximately 9%, exerting tremendous pressure against whatever material confined it. Flat thresholds created a collection point for meltwater. The horizontal surface allowed water to pool at the door base during thaw periods. When temperatures dropped, this pooled water froze and expanded. The expansion had nowhere to go but inward, prying door jambs away from threshold, splitting wood fibers, and forcing doors open from the bottom. Crossbars set at mid-height could not counter pressure originating at the floor. Raised thresholds with rounded exterior faces changed the ice dynamics entirely. Meltwater did not pool on a curved surface. It ran off. Water that did freeze along the threshold lip expanded outward and upward, following the path of least resistance along the curve. The ice fractured and lifted away from the wood rather than forcing its way into joint gaps. The same freeze-thaw cycle that destroyed flat threshold doors left raised thresholds largely undamaged. A Homestead maintenance log from the winter of 1880 to 1881 documents the difference quantitatively. Days lost to door clearing and repair dropped from an average of 1 day per week to 1 day per month after threshold modification. The homesteader noted, "Door opens freely most mornings." In contrast to the previous winter's notation, axe required 3 mornings of 5. The expectation was that ice expansion always moved inward, prying structures apart from the inside. The outcome recorded in comparative damage reports showed that ice expansion followed geometry. Flat surfaces trapped and directed it inward. Curved surfaces deflected it outward. The ice itself was not defeated. It was simply taught where to go. Homesteads throughout the region noted the pattern. Doors with raised, rounded thresholds remained operable during prolonged freeze periods that rendered flat threshold doors immobile. The difference was measurable in lost work time, in firewood wasted heating a structure that could not be properly sealed, and in simple daily function. Claw marks and shoulder scuffing marked the base of a cabin door at the Plains woodland edge, winter of 1880. The scratches ran horizontally across the bottom door plank, concentrated below 18 inches from the ground. The hinges showed no damage. The door frame remained intact. The door had held. Trapper records and settler accounts from the northern plains document bear behavior around structures during late fall and early spring. Bears investigated cabins, smokehouses, and storage buildings, attracted by food smells. Contact occurred predominantly at ground level. Bears pushed with shoulders and clawed with forepaws, both actions concentrated below knee height on a standing human. A flat threshold provided solid purchase for shoulders and claws. Continuous horizontal pressure could split door planks or tear hinges free. Raised thresholds with rounded exterior lips changed the contact dynamics. A bear's shoulder pushing against a curved surface found no perpendicular resistance point. The curve deflected pressure downward and outward. The shoulder slid off rather than gaining purchase. Claws scraped along the curve but could not grip effectively. Sustained pressure became impossible because the geometry denied the leverage needed to apply it. Damage pattern analysis from multiple homesteads shows a clear distinction. Doors with flat thresholds displayed interior damage, broken hinges, split jambs, and occasionally penetrated door leaves. Doors with raised, rounded thresholds showed exterior scarring, scratches and scuffs on the threshold lip and lower door face, but rarely showed structural failure. The door surface had been tested, but not defeated. The expectation among frontier builders was that crossbars provided primary defense against forced entry. A heavy timber beam set in iron brackets across the door interior would stop any intrusion attempt. This was true for latched or locked doors being struck at lock height. It was less true for unlocked doors or doors being pressured from the bottom, where crossbars provided no mechanical advantage. The outcome documented in comparative accounts showed that geometry reduced reliance on crossbars. Doors with raised thresholds resisted ground-level pressure even when unbarred. The threshold itself became a passive defense, requiring no human intervention to function. A homesteader checking livestock in the night could leave the door closed but unbarred, confident that the geometry provided reasonable security. This was not absolute protection. A determined grizzly could destroy any frontier door given sufficient time and motivation. But most encounters were brief investigations, not sustained assaults. Brief investigations encountered curved surfaces that offered nothing to grip, nothing to push effectively against, and no way to apply the leverage needed for entry. The bear tested the structure, found no purchase, and moved on. Backed-out hinge screws sat in a pile next to a frontier doorframe in December of 1880, somewhere in the rail-served settlements of Dakota Territory. The door had failed again. The soft wood jamb showed elongated screw holes where iron had pulled through wood fibers. The hinges themselves were undamaged. The wood had given way first. Hinges perform best under compression loading, when force pushes the hinge leaves together rather than pulling them apart. Iron resists compression extremely well. Its resistance to tension is lower, and its resistance to shear, forces acting perpendicular to the hinge pin axis, is lower still. A door subjected to bottom edge pressure on a flat threshold loads the bottom hinge in tension and shear simultaneously, the weakest possible. Loading combination. The raised threshold modification changed the load path entirely. When force struck the rounded threshold lip and deflected downward, it transferred weight through the threshold into the foundation or floor structure. Very little force reached the door leaf itself. The hinges no longer needed to resist horizontal leverage. They only needed to support vertical door weight, placing them in pure compression loading, their strongest orientation. Hardware store ledgers from settlements along the Northern Pacific Rail line during 1880 and 1881 provide quantitative evidence. Homesteads that adopted raised threshold designs ordered replacement hinges at approximately 1/4 the previous rate. The difference showed clearly in seasonal ordering patterns. Standard flat threshold structures ordered hinges in November and again in March. Raised threshold structures placed orders once every 2 to 3 years. The hinges themselves had not. Improved. The same blacksmith-forged straps with the same screw patterns served both applications. The hinges on modified doors were not stronger, heavier, or better designed. They simply experienced less destructive force because the threshold geometry intercepted and redirected that force before it could act on the hinge. Cost comparison showed significant savings. A pair of strap hinges cost $1.25 delivered. Installation labor added another 50 cents for a homesteader hiring the work done, or 4 to 6 hours of personal labor otherwise. Replacing hinges twice yearly cost $2.50 plus labor. Over 5 years, this accumulated to $12.50, more than enough to build an entire door from scratch, including frame, planks, and hardware. The expectation among frontier builders was straightforward. Better iron meant longer door life. The outcome recorded in ledger comparisons showed that better load paths mattered more than better materials. The geometry prevented damage rather than merely resisting it. New threshold construction occurred outside multiple homesteads in Dakota Territory, spring of 1881, while broken fences still lay unrepaired in the same yards. The priority seemed backward to outside observers. Fences protected crops and contained livestock. Doors merely closed. Yet homesteaders shaped thresholds first. Labor mathematics explained the decision. Shaping a raised threshold from hardwood scrap required 4 to 6 hours, 2 hours for rough shaping with a draw knife, 1 hour for smoothing, 1 to 2 hours for fitting and installation. Repairing a damaged door required 8 to 12 hours to remove the old door, source or mill new planks, reassemble, and rehang with proper clearances. Rebuilding section of fence required 2 to 3 days. The threshold modification prevented door failures that would otherwise require the 12-hour repair cycle multiple times per year. Material costs favored threshold modification even more strongly. A raised threshold could be built from salvaged hardwood, damaged wagon components, broken tool handles, or storm-felled timber. Cost: 0 to 15 cents for raw material if purchase was necessary. A replacement door required purchased lumber at 60 to 90 cents per door, plus hinge replacement at $1.25. Fencing required either cut posts at 5 cents each or split rails at 2 cents each, multiplied by linear feet needed. Freight considerations mattered significantly in isolated homesteads. Lumber, hardware, and wire fencing arrived by rail, then required wagon transport to individual claims. Freight delays during spring mud season could extend 6 to 8 weeks. A threshold could be built from materials already on site, eliminating freight dependence entirely. Store ledgers from rail depots along the Northern Pacific Line show an unusual pattern in spring of 1881. Plank sales spiked briefly, a single purchase per household rather than ongoing orders. Then purchases ceased. Hinge orders, which had been steady throughout the previous year, dropped dramatically. The pattern suggested a one-time material acquisition followed by long-term reduction in repair needs. The expectation embedded in frontier construction practice assumed major innovations spread slowly, requiring years of demonstration, word-of-mouth transmission, and gradual acceptance. Raised threshold adoption defied this expectation. The technique spread throughout affected regions within a single year. The speed of adoption indicated something significant. The method was immediately recognizable as superior, requiring no theoretical understanding to validate. Proof came from observation. A homesteader visited a neighbor's claim, saw a door that opened freely in January while his own remained frozen, asked a single question, received a simple answer, and implemented the modification within a week. No written instructions needed. No expert consultation required. The geometry explained itself through direct comparison. Frost formed on the interior surface of hinge leaves elsewhere in Dakota Territory, January of 1881. The metal was cold enough to nucleate ice crystals directly from humid interior air. The hinge had frozen tight. The door would not move. Residents remained trapped inside until the afternoon sun warmed the exterior enough to permit motion. Signal Service weather stations recorded sustained sub-zero temperatures across the northern plains throughout January of 1881. The temperature at Fort Yates remained below 0 degrees Fahrenheit for 18 consecutive days. Nighttime lows reached minus 32 degrees. Wind speeds averaged 15 to 25 miles per hour, creating wind chill equivalents below minus 50 degrees. These were not record-breaking conditions, but they were sustained, day after day without relief. Doors without raised thresholds failed in multiple ways during this period. Ice accumulation sealed doors shut from the exterior. Frozen hinges prevented movement even when ice was cleared. Wood contraction opened gaps around door frames, allowing wind-driven snow to enter structures. Homesteaders chopped ice from doorways each morning, losing an hour or more of productive time daily. Doors with raised, rounded thresholds remained largely functional throughout the same period. Ice that formed on the rounded lip fractured and fell away when the door was pushed. The setback jam prevented ice from sealing the door to the frame. Hinges experienced less stress because door movement required less force, reducing the work hardening and binding that contributed to frozen hinge failure elsewhere. A Homestead diary entry from the third week of January, 1881, records, "Door opens before first light. No axe needed fourth day running. Fire built without delay." The phrasing seems mundane but documents a critical survival advantage. Starting a fire immediately upon waking, rather than spending 30 to 60 minutes clearing a frozen door, meant the interior never cooled to dangerous temperatures during nighttime hours when fires burned low. Temperature records show that exterior conditions during this period could kill an exposed human in 15 to 30 minutes. Interior temperatures in cabins without sustained fires dropped to near freezing within 2 to 3 hours. The ability to quickly exit a structure, bring in firewood, and restart a fire without fighting a frozen door was not merely convenient. It was the difference between maintaining survivable interior temperatures and experiencing genuine cold-related danger. The expectation was that all doors failed eventually during extreme cold. It was accepted as inevitable. The outcome recorded in comparative accounts from the same winter, the same region, and the same weather. Conditions showed otherwise. Geometry delayed or prevented failure modes that seemed universal. Survival hinged, quite literally, on inches of threshold height and degrees of radius curvature. Ledger columns narrowed in county seat records during February of 1881. The entries tracking door repair costs showed declining numbers for homesteads that had modified thresholds the previous year. The comparison was stark. Repair costs dropped from an average of $4.50 per winter to less than $1. The savings accumulated beyond simple materials cost. Labor days lost to door clearing and repair decreased proportionally. A homesteader who had previously dedicated 1 day per week to door maintenance, clearing ice, rehanging hinges, patching split jams, now required intervention, perhaps twice per winter season. That represented 20 to 25 days of recovered labor per year. 25 recovered days translated directly to completed work. Otherwise deferred. Fences built, firewood cut and stacked, root cellars dug, equipment repaired. Or simply rest during a season when cold made every physical task more exhausting. The labor savings were not abstract. They represented tangible improvements in homestead function and resident survival probability. Material savings showed similar multiplication effects. Money not spent on replacement hinges, door planks, and carpenters' wages remained available for other critical needs: seed stock, livestock, medical supplies, or simply reserve funds against future emergency. $2.50 saved annually on door repairs equaled 50 pounds of flour or 10 pounds of coffee, substantive quantities in frontier household economy. The expectation embedded in frontier cost accounting was that winter damage represented unavoidable overhead. Budgets included line items for seasonal repairs. Homesteaders accepted that doors, like roofs and chimneys, required regular maintenance. Spending. The outcome documented in ledger comparisons showed that specific damage types were avoidable through design, rather than inevitable despite materials. A merchant's account book from a rail depot settlement shows the shift clearly. In winter of 1879 to 1880, the merchant sold 47 pairs of strap hinges to 32 homestead customers, an average of nearly 1.5 pairs per customer. In winter of 1881 to 1882, the same merchant sold 19 pairs to the same customer base, less than 1 pair per customer. The merchant noted declining hinge sales as a significant business impact. The statistical reality was simple. The cheapest component of door construction, the threshold geometry, which cost nothing but labor time to modify, had altered the economic equation for the most expensive component: iron hardware that had to be purchased and freighted from distant forges. Survival on the frontier was often determined by resource efficiency. Small savings compounded into significant advantages over time. A modification that cost 1 afternoon of work and saved 25 labor days plus $2 to $3 annually represented an extraordinary return on investment. Intact door frames stood throughout Dakota Territory after snowmelt in spring of 1881. Homestead inspection reports filed with county land offices document the pattern. Structures with raised thresholds showed significantly lower failure rates across multiple categories: hinge damage, jam splitting, sill rot, and ice damage. The winter of 1880 to 1881 had not been the coldest on record. Weather station data shows more severe winters occurred before and after, but it had been sustained. Months of repeated freeze-thaw cycles, weeks of sub-zero temperatures, persistent wind. The duration tested every structural element of every frontier building. Photographic evidence from the E period, though limited, shows raised threshold features appearing on homestead structures across the northern plains. Door frames photographed in spring of 1881 display the characteristic raised sill and setback jam geometry that had been uncommon 2 years prior. The visual record confirms written accounts of widespread adoption. The method had spread without formal channels. No agricultural extension service promoted it. No patent protected it. No commercial manufacturer sold pre-made components. The technique moved through direct observation and informal conversation. A neighbor saw a functional door during a week when his own door failed. He asked a question. He received an answer. He implemented the change. He became the next demonstration site. Winter itself had been the selection mechanism. Structures that incorporated the geometry survived with minimal intervention. Structures that retained flat thresholds required constant maintenance and frequent repair. The PAYO difference was visible, measurable, and immediately attributable to a specific modification. No theoretical understanding was required. The doors either worked or they did not. The expectation in frontier culture was that survival depended on individual toughness, the ability to endure hardship through strength and determination. The outcome documented in damage reports, repair ledgers, and comparative accounts showed a different truth. Survival depended on method as much as resolve. Two homesteaders of equal toughness experienced dramatically different winter outcomes based solely on threshold geometry. A county inspector's report from spring of 1881 noted, "Structures maintaining serviceable doors throughout winter showed lower incidence of livestock loss, reduced firewood consumption, and better overall condition. Door function impacts more than entry. It impacts heat retention, security, and operational efficiency." The observation was understated but accurate. AC door that opened freely meant fires could be tended promptly. A door that sealed properly meant heat was retained. A door that resisted ice and animal pressure meant less frequent emergency repairs in dangerous conditions. The threshold geometry had cascading effects throughout the entire structure's winter performance. Worn thresholds still held structural integrity across the northern plains into the 1890s. Wood that had been shaped a decade earlier remained in service, showing use polish but not failure. The geometry continued functioning because it required no maintenance beyond what the threshold would have needed regardless. The raised threshold method endured because it required no external validation. No governmental authority needed to approve it. No expert needed to certify it. No manufacturer needed to produce it. A homesteader could examine his neighbor's door, understand the principle in 5 minutes, and implement the change in an afternoon. The technique was entirely within the capabilities of anyone who could build a cabin in the first place. This accessibility explained the spread pattern. Methods that required specialized tools, purchased materials, or expert knowledge spread slowly and unevenly across frontier regions. Methods that used existing tools, salvaged materials, and observable logic spread rapidly. The raised threshold required only a draw knife, a tool every homesteader already owned for shaping shingles and fence rails. The modification also required no theoretical understanding to implement successfully. A homesteader did not need to comprehend leverage principles, stress loading, or thermal expansion coefficients. He only needed to observe that rounded surfaces deflected force and that raised surfaces changed contact geometry. The physics operated whether or not anyone understood them. Later, agricultural extension bulletins from the 1890s mention raised door sills in passing, describing them as common, practice without attribution or explanation. By the time formal agricultural education systems developed infrastructure to document and disseminate building techniques, the raised threshold had already become standard practice in regions where winter conditions warranted it. The knowledge had moved faster than institutions. The expectation was that innovations required official endorsement to gain legitimacy. The outcome showed that effective solutions required only visible results. A door that worked when others failed needed no credentials beyond that performance. Proof was the endorsement. Patent records from the period show no applications for raised threshold designs. The modification was not considered proprietary knowledge. It was considered obvious common sense once observed. This lack of patent protection meant no commercial interests formed around the technique. It remained a household modification, not a marketable product. The best frontier solutions often left minimal paper trail. They were too simple to warrant written documentation, too obvious to require explanation, and too cheap to generate commercial interest. They spread through demonstration and disappeared from historical record, even as they fundamentally improved survival odds for thousands of homesteaders. A ledger line from spring of 1882 reads simply, "Door, no repairs." The notation appears in a homestead account book preserved in county historical archives. Above it, entries from previous years list hinge purchases, plank replacements, and labor costs. Below it, entries continue for other maintenance items: roof, chimney, fencing. But the door line shows zero expenditure. That single ledger entry documents a broader shift in frontier building practice. The raised threshold, or bare lip as it came to be known colloquially, represented a category of solution that frontier conditions favored: geometry over strength, design over reaction, prevention over repair. The technique demonstrated principles applicable beyond door construction. Force could be managed through redirection rather than resistance. Small design changes could have disproportionate effects on structural performance. The cheapest modification was often the most effective if it addressed the root cause rather than symptoms. Quantified impact shows clearly in comparative records. Homesteads with modified thresholds experienced 70 to 80% reduction in door-related repair costs. Labor days saved averaged 20 to 25 per winter. Hinge replacement intervals extended from 6 months to 2 to 3 years. Ice clearing time decreased from 60 minutes daily to occasional intervention. These were not marginal improvements. They were categorical changes in door system performance. The broader lesson extended beyond thresholds. Frontier survival consistently favored those who understood mechanical principles over those who simply applied force. A homesteader who comprehended why a door failed at the floor could prevent that failure with an afternoon's work. A homesteader who only knew doors sometimes broke would spend money and labor fighting symptoms indefinitely. Modern construction incorporated these principles without attribution. Building codes require raised thresholds for weather sealing. Door jambs are set back from exterior faces. Threshold surfaces are shaped for water management. The bare lip threshold is not historically recognized because it became standard practice, invisible through ubiquity. The final record is not in ledgers or photographs, but in the structures themselves. Frontier cabins preserved as historical sites occasionally retain original door frames. Those that show raised, rounded thresholds with setback jambs mark places where someone understood geometry well enough to teach force where to go.